Hello, this is my lab report for lab 4 for oscillations. So here's the problem. The problem is to model the motion of a spring moving in 2 dimensions after it is released from rest. We'll watch and record as the spring oscillates and compare the computational models to determine its accuracy. The fundamental principles are Newton's second law, the energy principle, and the spring force. Newton's second law, here is Newton's second law, the position update formula, and the spring force right here. And here is the equation for the energy principle right here. So the organization will be looking at the tracker video and the produced point mass graph and the position in the X and Y direction, look at the computational model and closed script and what went into the model to make it work. We'll also discuss the discrepancies between the experimental position and the model position. And then we'll also answer the what does it mean questions, which are, is the energy principle satisfied? And compare the estimates of the period of oscillation between the X position data and the Y position data. So first, let's look at the tracker video. Here it is. So from the beginning, and here we can watch as the data is tracked. Here is the graph that is created. You can see it clearly oscillates. And here is the X position and the Y position data. So it runs from 0 to 9.5 seconds in 0.1 second intervals. As you can see here, 8.7 to 8.8 and so forth. The frame rate is 30 frames per second, but I had an issue where the video's quality seems to run at a slower rate. So I was forced to double or triple click at the same position sometimes instead of just once. So I resolved this by increasing the step size from 1 to 3, as seen right here. And that's what created the 1 second interval. And it also created a cleaner graph and data. And then we copy and pasted this X position and Y position data into a CSV file to use for a computational model. So now let's look at the computational model, which is right here. I chose option 1 personally to use that pre-made video, which came with a K for the spring constant of a 6.83 newtons per meter, L naught of 0.123 meters, and a mass of 0.402 kilograms. The initial ball position is the same as the initial position in the experimental data. And I calculated the needed elements for the spring force and energy, which was L hat, and S right here. We needed them for these equations, the spring force, the potential spring energy equation. And then it also calculated the initial energies and forces. We have force of gravity, which is mg, the potential gravity energy, which is mgy, and k equals half mv squared. Here's the code for that right here. And the total energy is equal to all 3 of these summed together because there is no work involved, because the system is defined as the mass and the spring as well as the entire Earth. And we also used Newton's second law to update the ball's position, velocity, and position, and updated the different energies involved and found the change in each of the energies. So we can see here F net, F spring, F grav, and here we have the different energies. And we plot that along with the position data. So let's run the code. So we pick our CSV file and we run it. So we're just going to let it run. And then we can see that the model and the experiment start out very close together, as you can see here. But as time goes on, we can clearly see that the experimental data actually starts to slow down compared to the model. So that begs the question, why is this the case? And the case is because possibly is that there are more forces involved, such as air resistance. And also we are assuming a frictionless spring, which is also unrealistic, which could cause the discrepancies that we see. So what does it mean? Question 1, is the energy principle satisfied? Well, we define work of the surroundings as 0 as we include the Earth along with our spring and the mass in the system. And this makes the equation delta E equals 0, where what we serve plus Q is equal to 0. And if we look at our change in energy versus time graph, we can clearly see that delta E, which is defined by the orange line, stays at 0 consistently, which satisfies our energy principles. And our other energies change as we would expect because, well, those energies would change as the spring oscillates with the ball attached to it, the ball of mass attached to it. So the second question is comparing the estimates of the periods of oscillation for X and Y. So let's go back to the tracker video and look specifically at this. So for the X direction, which is right here, we had 5 periods in a span of 8.2 seconds from here to here. So we divide 8.2 by 5 to get the average, which is 1.64 seconds, which will be our period for X. And we do the same thing for Y from this position, 0.7 to 8.2 over here, and which is 7.5 seconds divided by the 5 periods, which gives us 1.5 seconds as our period for Y. Now, clearly the period for Y is less than X by these estimates, but I think this can be attributed to the fact that at the start of the video, the mass looks more displaced in the X direction. Let's look, as you can see right here, than the Y direction. This causes it to swing in a greater amount in the X direction than the Y direction, resulting in a greater period. So if we watch this thing go, if we watch the video go, you can clearly see that the X seems to vary much more than the Y, which would cause the greater oscillation period. Thank you.